Hello, I'm Samir Sapra and I'll be teaching you the physical chemistry part of this course, CYL110, and all of the information related to the lecture material will be found at http://web.iitt.ac.in/CYL in capitals 100. So, one thing that I'll be giving you is lecture handouts, which you're supposed to read before you come to the lecture so that we can elaborate and discuss these handouts rather than going over the whole thing again. And two, there will be some questions for assignments and practice, which you do not have to turn in the practice questions, but they're just for practice for you. Okay. So, I'll be essentially teaching you thermodynamics, right? Thermodynamics, which is, as the words imply, that's the study of flow. Yeah, dynamics is flow of thermo or heat. So, when you affect changes, how does heat flow during these changes? That is what you have to study, and that has become essential sometime in the 1800s, in the beginning of the 1800s, when the Industrial Revolution came about, and then you had engines and fossil fuels, and you had to worry about all the efficiencies and stuff like that. Yeah. In fact, thermodynamics is very important also for everyday bodily functions, which we'll discuss in the course of this course. Fine. So the four laws of thermodynamics, right, is what matters the most over here. One is the zeroth law, right, and this defines temperature, and we'll just see today how it defines temperature. The first law, in fact, tells you you cannot get even, right? Yeah, so it says conservation of energy. You can't gain anything out of it. You can transform energy from one form to the other, but you cannot get any additional energy out of nothing. In fact, when Einstein brought in the mass energy equivalence, he did not disturb thermodynamics, right? He came into the framework of thermodynamics and still continued with the same laws of thermodynamics. So that's why thermodynamics happens to be quite basic and fundamental. The second law, which just says that, look, you can perhaps get even, but you have to go down to 0 Kelvin. Yeah, that essentially defines entropy, and we'll look at that in more details later on. And the third law, it just says that, okay buddy, you can, the second law told you that you can get even at 0 Kelvin, but no way, you're not going to reach 0 Kelvin. Yeah, it gives you a numerical value to entropy. Okay. So let's see. Some of the things that you've definitely done before, I'll just browse through them. Okay. So, you have the system and the surroundings, and everything that is not a part of the system is the surrounding, right? The entire universe is the sum of the system plus the surrounding. And you're mostly interested in what's happening in the system, but the surrounding does get affected. And the thing that separates the system and the surrounding is a boundary. it could be a real boundary, as it could be a container, right? It could be also an imaginary boundary which you've used to define the system. Okay, so the system could be open, closed, isolated. In the open system, you're allowing mass and energy to flow freely through the boundary. The closed system allows only energy to flow and not the mass, right? And then you have the isolated system, which is essentially separated from the surroundings, so that nothing can flow through, neither energy nor mass. Okay, so you have systems. Well, I'm just telling you these things, but you could read a bit more and brush up your backgrounds. You've done this all, right? So you have to define the system first. To define the system, you have to tell about the pressure of the system, the temperature, the volume, yeah, the number of moles of the system, the amount of the system, its mass, yeah. You have to tell what kind of a system it is. You have to completely define, essentially, right? How many components are there, right? So these are all the things. You could, for example, you're defining these properties. You could have intensive properties, you could have extensive properties, right? And that's important, because the extensive properties, they change as you change the amount of the system, or yeah. So for example, the volume would double if I double the system. The mass would double if I double the system. But if you think of molar volume, yeah, molar volume does not change. It remains the same even if I double the system. The temperature does not change, right? So there are some things which are extensive, some of these are intensive properties, right? Then there are state variables. So let me just write down these keywords so that you know what you are supposed to brush up. Yeah, intensive, extensive. Then you have state variables. Now, so these state variables are there, right? So for example, energy is a state variable. Now, no matter how you reach that point, yeah, that is so if you think of the potential energy at the top of the mountain, it doesn't matter how you climb that mountain, how much energy you spent, but the potential energy at the top of the mountain is exactly the same, no matter how that state has been reached, right? So there are these things called state variables, there are these things called path variables, and we'll use these things very, very extensively. Okay, and at some certain point of time, I'll also tell you some more examples of these state and path variables, definitely very, very soon. Well, although I'm not much of a purist, but then we have the chemical notation, which one must follow if one has to take into account and keep your track clean. So for example, if you wish to specify the state of a system, and you say, okay, I have 3 moles of the system. The system is nitrogen gas in brackets. I also need to specify the pressure, which is 1 bar, let's say, to start with. I need to specify the temperature, 100 degrees C. I think if I have specified these things, then my state is completely specified. Okay, I don't need any more information to define my state. Good. And I can go from one state to the other using various paths, right? So those would be your path variables. These paths could be reversible.